We're now going to study optimization theory. We'll start with basic definitions. That will cover the first of the 3 videos on this topic. Then we'll go on to discuss duality, continuous unconstrained problems, equality constrained problems, inequality constrained problems, before then studying integer problems, mixed integer problems, and there are a couple of homework exercises at the end of the slides. So to start with basic definitions, similarly to our definition in the context of simultaneous equations, when we consider optimization problems, we'll have a decision vector, and our goal is to pick a choice of a value of decision vector. We'll usually denote the decision vector by x or y or z, and it'll be chosen from the Cartesian product of real numbers n times with itself, or some subset that I'll denote by s of r to the n. And as previously, the entries of the decision vector are going to be indexed by subscripts. For example, when we consider economic dispatch, the choice of dispatch for generator k might be xk, for example, while the choices of dispatch for all generators is given by the vector x. An optimization problem has a decision vector. It also has an objective. An objective is a function, and I'll usually write f for that function. It will go from r to the n into r, and it will tell us, denominate, the cost or the lack of desirability of the solution x for a particular model, for a particular system, under a particular set of circumstances. So f of x is the cost of using x as the solution. That function f is called the objective function, and a good example in our field of interest is the operating cost of a generator, or the sum of the operating costs of all generators in the system is typically what we'll use for f. Here's an example of a quadratic function. I've graphed it, and you can see how the quadratic function looks in that graph. Turns out that whether a function is linear or quadratic is one way to categorize objectives, but another way, which actually has more unifying power, is will be discussed in section 4.1.14, and it involves the notion of convexity. We'll need to introduce some definitions to come to that way to categorize objectives. In addition to the decision vector, the objective, and we also have the feasible set. So typically, although some problems are unconstrained, typically problems involve restrictions of the choices of x. So we'll imagine a feasible set S, it's a subset of Rn, and we have to select our decision vector from that subset. So a good example would be the set representing the allowable range of operating conditions of a generator. We can think of that for all generators together, so the set representing the allowable range of operating conditions for all generators in a system. So putting that together, we get a minimization problem. Minimization problem means to find the minimum value of the function f of x over choices of x that lie in the feasible set S. So to make that formal, if S is a subset of r to the n, if f is a function that goes from S into r, and f star is some particular number, some particular real number, then when I write f star is equal to the min over x in S of f of x, that's how to pronounce equation 4.2. What I mean is there is some value of x, that backward e means there exists. There's some value of x star in the feasible set S, such that when I plug in x star to f, I get back f star. And furthermore, I can't do any better with any other feasible point. In other words, x being an element of S implies that f of x star is less than or equal to f of x. We say that f star is the minimum of f of x over x in the set S, and or f is the minimum of f of x such that x is in S. Here's an example paralleling the earlier examples. I want to find the choices of dispatch x for all generators that minimizes the sum of the operating costs such that the dispatch meets the demand and such that the generation is within the allowable operating range for the generators. So that in fact is our economic dispatch problem. my definition of minimum focused on the value of the function, but sometimes I'm interested in the choices of x that minimize the function. And for that, to describe that, I'll define the following notation. The set of all minimizers of a problem is denoted by argmin of x in S, of f of x. Argmin means the argument of the minimum. X is the argument of the function f. If the problem has no minimum, it doesn't have any minimizers, then the argument is the empty set. Often I want to emphasize the role of S, and so I will have slight variations on the notation I've just presented. For example, the min over x in Rn of f of x such that x is in S. So that vertical line means such that. And so when I want to emphasize the role of S, I'll write such that x is in S. And if S is defined as a set of points satisfying a particular criterion, we'll sometimes write out that criterion explicitly. So very often we're going to consider optimization problems with an objective F, but with a feasible set that's defined in terms of functions G that goes from Rn into Rm, and function H that goes from Rn into R to the R. And my feasible set will be defined as the set of x's in Rn such that g of x is equal to 0 and such that h of x is less than or equal to 0. And in that case, we might write out the min over x in Rn of f of x such that g of x equals 0 and h of x is less than or equal to 0. To visualize some of these optimization problems, I want to define a useful graphical technique that's based on the so-called level and contour sets. So let's suppose S is a subset of Rn, F goes from S into R, and let me write F tilde for some particular number in R. Then I'll define the level set of value F tilde of the function F is the set of x's such that f of x is less than or equal to f tilde. On the other hand, the contour set is the set of points such that f of x is exactly equal to f tilde. The idea of a contour set generalizes our notion of a contour map. So the contour set generalizes our notion, or is analogous to our notion of a contour map that you might use if you were exploring some terrain. And just like a contour map, contour and level sets are very useful for visualizing functions. So let's have a look at an example. Here's a function defined by f of x is equal to x1 minus 1 all squared plus x2 minus 3 all squared. It's kind of difficult to visualize, but if we look at its contour set, which I've shown in this figure, you can see that the contour set is a collection of concentric circles. So I've drawn here the contour sets at various levels or values. F tilde is 0, which is the dot at the center, 2, 4, 6, and so on. So the nice thing is that a contour set can be shown in one less dimension than the graph of the function. So for a function that goes from r squared into r, the graph of it requires a three-dimensional plotting. The contour set only requires a two-dimensional representation. And if it's not clear from the context, it's usually useful to explain which way the contours decrease. So in this case, the contours decrease towards the point 1, 3. So let's now, armed with some definitions, some basic definitions, now define our various types of optimization problems. So the feasible set is actually the whole of Rn. If S is not a strict subset of Rn, but the whole of Rn, then we say that the problem is unconstrained. And so if we look at the objective that was introduced in 4.4, f of x is equal to x1 minus 1 all squared plus x2 minus 3 all squared, then figure 4.3 shows the contour sets, and just looking at that figure, if we look at that figure, it's clear that the lowest value of the objective is right where that dot is at the point 1, 3. And so the minimizer, is the set that consists of the single point 1, 3, and plugging that value into f, we get f star is equal to 0. There's a minimum f star equals 0, a unique minimizer of this problem. The next step up is when we add some constraints that are defined in terms of equalities. So let me suppose that g is a function that goes from Rn into Rm, and we'll define the feasible set to be the set of x's in Rn such that g of x is equal to 0. That problem is said to be equality constrained. And the power flow equations, we met that back in section 3.2.7, is an example of equality constraints. And generically, equality constraints arise when we've got a mass balance or a flow balance type constraint. If the equality constraints are linear, that will occur if g is affine, in other words, of the form ax minus b, and a good example of that is our DC power flow approximation to the power flow equations. So using the objective we've met before, but setting g of x equal to x1 minus x2, then if I require that equal to 0, I have the equality constraint problem shown in equation 4.5. And it's easy to see the solution of this problem if I redraw the contour sets, but then additionally draw a set representing the feasible points. That's that diagonal line there on the graph. We can then think about finding the contour of the lowest height that lies on the feasible set. And I've illustrated that again with a bullet, and that bullet is at the point 2, 2. So the set, the minimum of my quadratic objective over points that lie on this diagonal line here is given by the objective at this point, and that objective, that point corresponds to 2, 2, and the objective has a value 2. In general, however, g might not be linear or affine, it might be nonlinear, and in that case we say that the problem is nonlinearly constrained. If we use the AC power flow equations as our equality constraints, then that would be an example of nonlinear equality constraints. So for example, same objective as before, but now I'm going to let g be x1 squared plus x2 squared plus 2x2 minus 3, and consider the equality constraint problem minimize x over Rn of f of x subject to gx equal to 0. If I draw my contour sets again and now draw my feasible set, the feasible set is the circle that you can see on this picture, and again I've drawn as a bullet the lowest contour. So remember, the contours decrease towards the center of the circles. That flows from the definition of the function, and the lowest contour that stays on the feasible set is this point here, and that corresponds to the point x star is equal to 0.5, 0.9. If in addition to equality constraints I also have inequality constraints, then I call the problem an inequality constraint problem. So my set is of the form x in Rn such that gx is equal to 0 and hx is less than or equal to 0. The line flow inequality constraints is an example of inequality constraints. If h happens to be affine, then just like the case of g being affine, we say that the problem is linear constrained, in this case linear inequality constrained. And a good example of that is our DC power flow approximation to the line flow constraints. They're examples of linear inequality constraints. If both g and h are affine, and if the objective is linear, then the problem is called a linear program or a linear optimization problem. Here's an example. F of x is equal to x1 minus x2. G of x is equal to x1 plus x2 minus 1. H of x is equal to minus x1 minus x2. If I require hx less than or equal to 0, that's the same as requiring x1 greater than or equal to 0, x2 greater than or equal to 0. And the following figure illustrates this problem. The lines, the parallel lines, show the contour sets in this case, and they decrease in the left-hand direction and going up. The equality constraint requires x1, x2 to lie on the line that I've shown part of here that is sloping perpendicularly to the contour sets of the objective. The inequality constraints require x1 to be greater than or equal to 0. That means that x1 has to live to the right of the x2 axis, and requires x2 to be greater than or equal to 0. That requires x2 to live above the x1 axis. So imposing them together, x1 and x2 live in the non-negative quadrant, and that means that the feasible set is the line segment, part of the full line, that lies in the non-negative quadrant, and finding the minimum contour on this line segment pushes us up against this point x star is equal to 0, 1. So when we have a linear program, we often emphasize the linear and affine functions by writing them out explicitly. So typically we'll write a linear program, a linear problem in the form C transpose x, minimize x over r squared, C transpose x subject to ax equals b and cx less than or equal to d. C is a vector in Rn. A is an m by n matrix, B is a m vector, C is an r by n matrix, and D is an r vector. And again, superscript dagger means transpose. So C superscript dagger means the transpose of C. So the problem 4.7 that we just met, which I wrote out in a general form that would also be capable of representing a nonlinear program, if we specialize that to the values of C, A, B, capital C, and D, that would specify that linear program. That's given by these vectors and matrices here. And we can write that even more simply because it's non-negatively constrained by simply writing x greater than or equal to 0. So I'll use these types of notations and their variations when they're appropriate. As it happens, linear programs are very well developed. There's a rich body of literature on linear programming, and linear programming software is very, very capable. The best known algorithms are the simplex algorithm, which was invented in the mid-1940s, and then more recently developed interior point algorithms. Reliability and capabilities of commercial linear programming code software are actually there's a number of reasons why we tend to use linear programming whenever possible, and that means that even when our underlying constraints are not linear, we'll often linearize them. For example, linearize the power flow equality and inequality constraints because the software is so well developed in comparison to software for tackling general nonlinear problems. I'll mention just a few other variations. If Q is quadratic and G and H are affine, then the problem is called a quadratic program or a quadratic optimization problem. In some cases, quadratic formulations are better matched to electricity market formulations. So we'll often think generically of electricity market formulations expressed as quadratic programs. In practice, they might actually be solved with a linear approximation, however. So here's an example: quadratic objective, linear equality constraint, linear inequality constraint. And I illustrated that here. Here are my contour sets. Again, the contours decrease towards the center of these circles. The equality constraint requires the points to lie on the line, and the inequality constraint requires x2 to be greater than or equal to 3, which requires x1 and x2 to lie on the half line segment that starts at this point and goes in the rightwards and upwards direction. And if I look at the lowest value contour that's on the feasible set, that's again represented by my bullet and is at the point 3, 3. And the value of the objective at that point is 4. The argmin is the singleton, single element set that consists of the single point 3, 3. And again, just with linear programs, we'll sometimes emphasize the quadratic nature of a quadratic program by writing it explicitly in this form. The equality constraints and inequality constraints are expressed in the same way as a linear program, but now we have a quadratic objective, so in addition to the linear term, we have a quadratic term. Typically, we'll omit the constant term in the objective because that does not affect the minimizer. For our problem 410, the appropriate vectors and matrices are exhibited there. If we don't have any restrictions on f, g, and h, then the problem is called a nonlinear program or a nonlinear optimization problem. When we want to minimize production costs subject to nonlinear power flow constraints and nonlinear line flow constraints, that problem is called the AC optimal power flow problem, and we're going to formulate that in section 9.1. So as an example, I could have a quadratic objective. I could have equality constraints that have nonlinear terms in them, such as sines. Remember that there are sign terms in our formulation of the power flow equations, and inequality constraints that have signs in them. And remember that our nonlinear formulation of the line flow constraints have trigonometric expressions in them. So in that case, we would have a nonlinear problem. So although I've organized problems in terms of linearity or nonlinearity, we'll see in section 4.1.14 that we can also classify problems on the basis of convexity. And very often convexity is a more useful way to think about the difficulty of solving a problem. So when we've got inequality constraints and we have a feasible point, the feasible point might satisfy those inequality constraints with equality, or it might satisfy them with strict inequality. So let's consider h, a function that goes from Rn into R to the R, and consider a particular entry of h. Let me think of h sub L, and a particular corresponding inequality constraint, h sub L of x is less than or equal to 0. We call that a binding constraint or an active constraint at a point x star if, when I plug in x star to it, hl of x star is exactly equal to 0. It's non-binding or inactive if hl of x star is strictly less than 0. And to keep track of that, I'll define a set called the set of active constraints, or the active set. I'll denote it by a of x star. Implicitly, we need to know the inequality constraint function. A of x star is the set of indices of the constraints. So it's the set of L's in the set 1 to R. Each of the constraints, HLX less than or equal to 0, is indexed by the index L of H. And what I want to do is pick out that subset of the full set of indices corresponding to the constraints that are satisfied with equality. In other words, the active set is the set of L's such that H sub L of x star is 0. And as I said, that's called the active set for hx less than or equal to 0 at x star. Let's see an example. H of x is 3 minus x2, x1 plus x2 minus 10. The first constraint requires that 3 minus x2 is less than or equal to 0. In other words, x2 is greater than or equal to 0. That requires my points to lie above this horizontal line. The second constraint is that x1 plus x2 minus 10 is less than or equal to 0. That requires my set of points to lie below and to the left of this line. And the set of points that satisfy both constraints is this eighth plane that is shown here in yellow. Part of it is shown in yellow. It extends to the left. I've illustrated 3 points, x star, x double star, and x triple star. If I look at the active set of x star, well, neither of the two constraints are binding. So the active set, which consists of the indices of constraints that are binding, that set is empty. The active set for x star is the empty set. For x double star, exactly one of the constraints is binding, and that is the first constraint. So the active set for x double star is the set consisting of index 1. For x triple star, both of my constraints are binding, so the active set in this case is the set consisting of index 1 corresponding to the first constraint and index 2 corresponding to the second constraint. So the reason why it's significant to us is that it is typical for some, but not all, of the inequality constraints in a problem to be binding at the optimum. And in fact, identifying which constraints are binding at the optimum or minimizer is, we could say, the key issue in inequality constrained optimization problems. So let me summarize this section by observing that for small example problems, we can look at a diagram and that can yield a minimum and minimizer. We're actually going to be interested in larger problems where the dimension of x is much larger than 2, and perhaps the dimension of g or h is much larger than 2. The geometry becomes much more difficult to visualize in this case, and although diagrams can help us, the intuition we get from such diagrams can become less reliable. So for those larger problems, we're going to use special purpose software to find the minimum and minimizer. An example of such special purpose software is the PowerWorld Optimal Power Flow Solver. It's an example of special purpose software that's particularly tailored to power systems optimization problems. MATLAB Optimization Toolbox, which you might use for some of the homework exercises, is an example of software that's tailored to more generic optimization problems. To consider the various types of problems, we sometimes need to be able to formulate a problem, but at the outset we may not know whether that problem has a minimum or not. And so to enable us to define a problem without knowing whether or not it has a minimum, I want to make a slightly more general definition than our notion of a minimum, and that general definition is the notion of an infimum, and I'll denote it by inf of x in S, just as the min denotes the minimum. So the infimum is defined as follows. The inf of a problem, the inf over choices of x in S of f of x, is the following. If my problem has a minimum, then the inf is equal to the minimum. However, in the case where it doesn't have a minimum, the conditions depend on the particular characteristics of the problem. Sometimes a problem will have a lower bound. That is to say that although there won't be a minimizer, I can find a value such that the objective evaluated at points in the feasible set never gets below that bound. If we can find such a bound, it's called a lower bound to be explicit. In fact, there will typically be multiple lower bounds, and we can think of finding the greatest or largest lower bound. That notion is always well defined because of results relating to the set of real numbers. So the inf is defined to be the greatest lower bound for the minimum if the minimum is bounded below. That will correspond to the minimizer if the problem has a minimum. On the other hand, if the problem is unbounded below, which means that no matter how small, how negative a number you have, I can always find a feasible x such that f of x is smaller than the number you nominated. Notionally, we can find values of x that make the objective smaller and smaller and smaller. And in that case, we're going to define as the inf the special symbol minus infinity. So it corresponds to the idea that somehow the best we could do with our problem is minus infinity. On the other hand, if the problem is infeasible, there is no x's in the feasible set, then no matter how high the bound was, how high a number was, it still wouldn't be a bound on the minimum. So in that case, we'll use another special symbol, infinity or plus infinity, for the inf. So just to summarize that, the inf is equal to the minimum of the corresponding minimization problem if the minimum exists. The infimum, however, exists even if the problem has no minimum. If it's bounded below, it'll be the greatest lower bound. If it's unbounded, it'll be minus infinity. If it's infeasible, then it will be equal to plus infinity. Let me give an example. Let's suppose I have an unconstrained optimization problem to minimize the function that goes from R into R given by, for all x, f of x is equal to x. I hope everybody can see that no matter how low a number you come up with, I can always find an x such that when I plug x into f, I'll get a lower number. You give me a number, I set x equal to that number minus 1. Then f of x will be equal to that number minus 1, and so it'll be lower than the number you might have suggested as a bound. In other words, there's no f star such that for all x in R, f star is less than or equal to f of x. That's just restating the fact that the unconstrained minimizer of f is actually unbounded below. If you check our definition, that means there's no minimum, but there is an inf. The inf is by definition minus infinity. Similarly, if the feasible set was so limiting that there was no feasible points, the inf would be plus infinity. As well as minimizing, we'll sometimes need to maximize, and a maximum of a problem is just minus the minimum of minus the objective. So mostly we'll focus on minimization problems, but with the understanding that maximization is essentially similar. And similarly, or paralleling the notion of inf for a minimization problem, there's also the notion of the supremum for the maximizer. So the sup, the supremum of a maximization problem, is given by the least upper bound for the problem if the problem is bounded above, plus infinity if it's unbounded above, and minus infinity if it's infeasible. And again, the sup is equal to the max if the corresponding max exists, but it generalizes it to in the case where the maximum does not exist. Several more definitions, in particular characterizing solutions of optimization problems. If we go back to our original definition of minimization problem, a minimum of a problem f star, it's equal. We denote it by the minimum of x in s of f of x. Sometimes we call f star the global minimum of the problem. That emphasizes that there's no x in S that has a smaller value of f of x, but is already implicit in our definition. But the notion of global is to be contrasted with the notion of a local minimum and minimizer. I need to introduce the notion of a norm. A norm is a measure of a vector, and I'll denote it by a pair of pairs of lines. If I've got a feasible set and a point x star in S, we say that x star is a local minimizer if there exists a tolerance epsilon such that for all feasible x in S such that x is within the tolerance epsilon of x star according to the norm. In other words, the norm of x minus x star is less than epsilon. If any feasible point that is close to x star has the property that its objective is no smaller than f of x star, then f of x star is called a local minimum and x star is the local minimizer. Another definition, if S is an element of Rn, we say that S is a convex set, or that S is convex, if for any two test points, x and x primed in S, and for any number in the interval 0 to 1, when I evaluate 1 minus t times x plus t times x prime, that is in S. If I've got 2 points, x and x primed, and I vary t between 0 and 1, the set of points 1 minus t times x plus t times x primed traces out the line interval that joins between x and x prime. So the definition of a convex set says that for every pair of points in the set, a line segment joining those pair of points is itself, the line interval is itself entirely contained in S. So here's some examples of convex sets. Each of these 4 sets is convex. I have illustrated two particular points in each of those sets and shown a line interval joining those points. To be a convex set, the line interval has to be inside the set for every pair of points. I've just shown it for one pair of points, but you can imagine each end of that pair ranging over all points in the set, and you can see that the line intervals in each case would be entirely contained within the set. On the other hand, these sets are non-convex sets. So non-convex sets typically have indentations like this set, which is kind of like a starfish, and these sets. In addition, if I take the union of two non-overlapping sets, such as the union of any of the convex sets on the previous page, that new set formed as the union will be non-convex. So let's connect together the notion of local minimizers and minimizing over a set. Here I've got a set S, that is the set of points x in Rn between -4 and +4, and I have an objective illustrated by the graphed by the solid line. You can see that this point that I've shown as a bullet at x double star equals -3, and this other point that I've shown as a bullet, which is at x star equal 3, are both local minimizers of the function. That's because if I pick a tolerance, let's say epsilon equal to 1/2, and I use the standard absolute value as the norm, if I look at points that are within 0.5 of 3, their objective values are all greater than or equal to the objective value evaluated at x star equal 3. Similarly, if I pick epsilon equal to 0.5 and I look at values of x that are within 0.5 units of x double star equal -3, then you can see again that the objective values are greater than or equal to the value of the objective at x double star. However, x double star is a local minimizer but not the global minimizer. The point x star is both a local minimizer and it's also the global minimizer. On the other hand, the point x hat equal 1.5 is not a local minimizer, and this height here is not a local minimum. Why is that? Well, again, if I pick tolerance 0.5, you can see that there are points that are lower in objective than x hat, but if I pick tolerance equal 0.25, there are values of the objective that are lower, and in fact, no matter how small I pick my tolerance, I will always find values that are within that tolerance of x hat and which have lower value of objective than f evaluated at x hat. In particular, I just pick a point that is to the right of x hat, slightly larger than x hat, but within the tolerance. On the other hand, if I change my feasible set, so if I change my feasible set to P, where P is the set of points x is between -4 and 1 and between 2 and 4. Notice that this set is a non-convex set, because if I pick a point over here in the left and a point in the right-hand part of the set and draw a line segment between those 2 points, that line segment will include points that are between 1 and 2, which are not in the set P. So my set P is a non-convex set. I've shown my function, I've graphed my function just on the feasible set, and you can see that x star is still a local, and in fact also the global minimizer. X double star is still a local minimizer, but changing the feasible set now has created a new local minimum and minimizer. In particular, x triple star is equal to 1. And the argument there is if I pick a tolerance, let's say 0.5, then notice that the feasible points that are within 0.5 of x triple star, in other words, does not include any of the points to the right, but includes the points to the left, all have objective value greater than or equal to the objective at x star. So the feasible set helps to determine the set of local minimizers, and in fact the set of global minimizers too. Generally, our problems have higher dimensions, so let's see an example of local minimizers over a non-convex set in higher dimension. I've got my my quadratic function. I've drawn its contour sets. The contours decrease towards the center of the circle, but my feasible set is going to be this shaded region. So here I've drawn my feasible set, I've drawn my contours of my objective not only on the feasible set but over all r squared, but I've shaded the feasible region. And you can see that if I want to find the lowest contour on the feasible set, there is actually two candidate points. Again, I've shown them with bullets. This bullet point that is x star roughly equal to 2.4 minus 0.1 is the global minimizer. But this other point here at, roughly speaking, 0.8 minus 0.7 is a local minimizer and not a global minimizer. The significance of the issue of a local versus a global minimizer is that we will generally use, for these sort of problems, a type of algorithm that is called an iterative algorithm that basically starts with an initial guess and over subsequent steps or iterations improves that step, typically by moving in space, moving within the feasible set in such a direction as to improve the objective. So imagine, for example, that I started with an initial guess, say around about here where I'm drawing the cursor. If we apply an iterative improvement algorithm to this problem, what we'll tend to find is that the sequence of iterates moves and heads towards this particular local optimizer, and we may not have good insights that it's a local minimizer and not a global minimizer. In contrast, if we started at an initial guess over here where I am showing my cursor, then it's reasonable, it will depend on the details of the algorithm, but it's reasonable that it might converge to the local minimizer. So the significance of a non-convex set is that when we apply a typical algorithm is that we're typically generating a sequence of successively better points, and consequently with an iterative improvement algorithm we're only going to be able to guarantee at best that we're moving towards a local minimum minimizer. If there are multiple local minimizers, then we may not be able to guarantee that we can get the global minimum of the problem. Even if we find a global minimum, it may be the case that there are multiple minimizers. And here's a good example. This function, my feasible set is, let's say, x between minus 4 and 4. That's a convex set. My function is graphed here as the solid line. And you can see that the minimum value is f of x equal to 1. And many points, in fact all of the points between minus x equals minus 1 and x equals plus 1, in fact achieve, or when plugged into f, yield that minimum value. So there are multiple minimizers. That can be the case even if the minimum is global. So how can we put all this together? To put this together and unify it, I want to introduce the notion of a convex function. The notion of a convex function relies on a convex feasible set. So let me start with S being a convex set. S is a subset of Rn. And let's suppose f is a function from S into R. We say that f is a convex function on S if for all points x and x primed in S, for all points t between 0 and 1, when I plug in the point 1 minus t times x plus t times x prime, that's a point on that line segment between x and x primed. By the way, that's the reason why we need S to be a convex set, and we need F to be defined on S, because I want to plug in points that are on that line segment. When we plug in points on that line segment, the value of F is less than or equal to 1 minus t times f of x plus t times f of x primed. Geometrically, that says that the function evaluated at a point on that line segment lies below the linear interpolation of the points, of the values of the function at the end points. So if f is convex on a test set that's given by the whole of Rn, we just say that f is convex. If we've got a multi-dimensional function, a vector function, I should say, h that goes from S into R to the R, we say it's convex on S if each of its components is convex on S, and it's convex on the whole of Rn if each of its components is convex on the whole of Rn. The set S in this context is called the test set, and we say that f is strictly convex on the test set if when we plug in any point on the interval that's not at the end points, that is to say, t is strictly greater than 0 and less than 1, and also assuming that x is not the same as x primed, we find that the value of the interpolation is strictly less than the value the value at the interpolated point on the line segment is strictly less than the interpolation of the values. So the condition means that linear interpolation never is below the function values. I've got a function shown here. I've got a pair of points that are in my set S, and the dashed line shows the linear interpolation. Convexity requires that for each pair of points, the function value, that's the solid curve, is below the linear interpolation. When I'm at a flat region, what will generally happen is that the linear interpolation will be coincident with the function. I've drawn my linear interpolation slightly off the function here for clarity, but they should be coincident. So for this function is convex but not strictly convex, because if you consider these two test points, x equals 0, x equals 1, the interpolation is not strictly above it. Again, let me emphasize, I've drawn it as being slightly above it, but in fact the interpolation would be coincident with the curve. So if S is a convex set and f is a function from S into R, we say that f is concave if minus f is convex. So what are some examples? If I have a linear function or an affine function, it's both convex and also concave on any convex set. The function that I showed in 4.11, that's this function, is not convex, and the reason for that is, for example, if we interpolate between x star and x double star, the linear interpolation will, for some of the points on the line segment between x star and x double star, we'll find that the line segment is not at or above the actual function. In other words, we don't satisfy the basic convexity definition. As a general observation, qualitatively, convex functions are bowl-shaped, and they have level sets that are convex sets. So remember, level sets are the set of points for a given level, such that the set of points x, such that f of x is below that level. Convexity is very important to optimization problems because of the following theorem. If S is a convex set and f goes from S into R, then if f is convex on S, then it has at most one local minimum over S. You'll remember that I observed that iterative improvement algorithms at best can guarantee that we converge to a local minimum. So if f is convex, that's fine, because we're only going to have one local minimum. If f is convex on S and it has a local minimum, then the local minimum is the global minimum, in other words. And furthermore, if f is strictly convex, then it has at most one minimizer. So the notion of convexity is so important that we'll even think of problems that have the particular property as being a distinguished class of problems. So I make the following definition. If S is a convex set, if f is convex on S, then the minimum of x over S of f of x is called a convex problem. What's an example of a convex problem? Well, if f is convex, if g is affine as a function, and if h is convex as a function, so if f is a convex function, if g is an affine function, if h is a convex function, then the set defined in terms of gx equal to 0 and hx is less than or equal to 0 will be a convex test set, and moreover, if f is convex on the whole of Rn, it will also be convex on the feasible set f, and so that means that my problem minimizing over choices of x, of f of x subject to g of x equal to 0 and h of x less than or equal to 0 is a convex problem. Theorem 4.1 tells us that a convex problem has at most one local minimum, but if we find a local minimum, it is indeed the global minimum, and as I've said a couple of times, iterative improvement algorithms can at best find local minima, but if we have a convex problem, they can find the global minimum in principle. In contrast, non-convex problems are generally much more difficult to solve. And we need to consider this in detail because some of the problems we need to solve involve integer variables. In particular, when we have problems that involve commitment of generators, they involve integer variables. How would we characterize a convex problem? Well, there are tests for convexity of a function that involve the first derivative of the function, and also tests that involve the second derivative. The first derivative test is as follows. Let S be a convex set. Suppose that f is partially differentiable with continuous partials. Then f is convex on S if and only if for every pair of points in S we have that f of x is greater than or equal to f of x primed plus the gradient of f of x prime transpose times x minus x primed. We've seen that right-hand side of 416 before. In fact, the function on the right-hand side, if we think of it as a function of x, is in fact the first-order Taylor approximation to f linearized about x primed. So the first derivative test says that a function is convex if and only if the first-order Taylor approximation is always at or below the function. I've illustrated that in this graph. Here I've illustrated two particular points, x equals minus 2 and x equals 3. The first-order Taylor approximation about x equals minus 2 is shown by the dashed line. The first-order Taylor approximation about x equals 3 is shown by the dotted line, and you can see that the first-order Taylor approximation in both cases is below the function. It never overestimates the function. There are also tests involving the second derivative, which are, in practice, easier to use. They involve positive semi-definiteness of the matrix of second derivatives of f, and that matrix of second derivatives is called the Hessian, and it's denoted del squared f, or when we're emphasizing the role of the argument x, I'll sometimes write subscript xx, del squared subscript xx of f. So in particular, the theorem says that if S is a convex set and f is twice partially differentiable with continuous partial derivatives on S, if we suppose that the second derivative, del squared f, is positive semi-definite throughout S, then f is convex on S, and if del squared f is positive definite throughout S, then f is strictly convex throughout S. So that completes our basic definitions of continuous optimization and notions of convexity. We'll go on in the next video to develop some of our underlying understanding of problems through the notion of duality.